Okay, so for part A here, obviously we just want to draw a free body diagram of the system. I am going to keep the masses separate on that diagram because part B requires us to separate the masses. Okay, so we have a 250 kilogram log attached by a chain to a 150 kilogram log, okay, that is being pulled this direction by 2,600 newtons worth of force. Right? We also know that in total, there's 2,400 newtons worth of friction on the entire system. So can I calculate the net force right off the bat then? I got 2,600 forward, I got 2,400 backwards, my net force is 200 newtons. Okay, so I know my net force is 200 newtons, and I know the mass of the system that 200 newtons is pulling on is 400 kilograms. So the acceleration of either log, both logs, the entire system is going to be 200 newtons divided by 400 kilograms, right? Which gives us the acceleration they list there, 0.500 meters per second squared forward. All right, now you need that number for part B. You can solve part B with either log, but you can't solve it as a system. Okay? It does have to be separated. All right, give you a few more minutes to see if you can figure out part B. All right, so as I said, you can solve this with either log, but the best bet is log A because log B is going to require one more calculation. It's not a hard calculation, but it requires one more step, and we have more information about log A. So we're going to look at just log A. So it's 150 kilograms. It's being pulled forwards by 2,600 newtons. They tell us that the force of friction back on log A is 900 newtons. What's the other force pulling on the first log? No, we need a force. What's forces? Well, there's another force pulling back on it. Right? Yeah, log B. Okay, log B is resisting it, right? If you're pulling on the first log, you can feel both. Okay, logs being there. So the other force is the force of B on A, and that's what the question wants us to find. Okay, is that other force? How much force is log B exerting on log A? So can I calculate the net force on this log using this number? Okay, mass times acceleration, right? So that's my next step. All right, the net force on log A will be mass times acceleration, so that'll be 75 newtons forwards. All right. I can also calculate net force using the sum of all forces. So F net will be the tension in the chain, 2,600 newtons, plus the force of friction, negative 900 newtons, plus the force of B on A, which is what we're looking for. All right, so I'm going to isolate that because I know the other three numbers, and I'm going to have that the force of B on A is F net minus the tension minus the force of friction. So that'll look like this: 75 newtons minus 2,600 newtons minus negative 900 newtons, okay, because it's backwards. Everybody all right with that? Okay, these two are forward, so I've made them positive. Okay, so we will have 75 minus 2,600 plus 900. Right, gives us 1,625. We only have three significant figures, so 1.63 times 10 to the 3 newtons, and that'll be backwards because that's the direction that log B is pulling on log A. All right, so it was really just a Newton's second law problem. Had I solved it using log B, it would have become a Newton's third law problem, because then I would have had to say, all right, I'm solving for the force of A pulling on B, and then I would have to reverse it to get what the question wanted. All right, everyone kind of follow there. Right? Really, from a Newton's second law perspective, we've done far harder questions than that. Right? But there's a lot more of the intuitive stuff that we said has been going on in these problems in this question. Okay, this is a relatively easy Newton's third law question, but I want you to give it a try. Okay, it's nothing like the logs and the boxes. It's much simpler than that. So just give it a try here. We're looking for the mass of one of the students. All right, so Newton's third law says that for every action, there's an equal and opposite reaction. Okay, what we know in this question is that there's two students, one's 38 kilograms, the other's mass is unknown, right? So we're going to say then that the mass of student 1 times the acceleration of student 1 equals negative mass of student 2 times acceleration of student 2, right? The numbers we have are the rates of acceleration for both and the mass of the first student. Sorry, they say A and B. All right, we'll say A and B, okay? A. All right, so if I'm looking for the mass of student B, really what I need to do is bring the acceleration of student B. Come on, go away. Okay, bring the mass of student B over, sorry, the acceleration of student B over to this side. All right, so it's going to cancel there and come over here, and now I'll have the mass of student B. Now I'm going to get a negative number. That's fine. Okay. In fact, I can eliminate this negative as long as I don't make this acceleration negative. Everyone follow me? Because that acceleration would have to be negative compared to A's acceleration. Okay, so I'm going to have 38 times 0.6 divided by 0.75. Right, and that's going to give me the mass of the second student. So 38 times 0.6 divided by 0.75. So the mass of the other student is 30 kilograms because we only have two significant figures. Okay, questions on that one? Right. Well, either way, it's both of them have two significant figures. 3.0 times 10 to the 1 is fine, so is 30. They both have the right number. All right, so what I want you guys to work on right now is not that, okay, is these four. We just did the first one, okay, so do 2, 3, and 4. They're Newton's third law problems. Okay, I'm going to give you a few minutes to work on those, see if there's any problems, and then we're going to finish up all the Newton's second law stuff. Okay, so for number 4, we're throwing this rock, okay? The masses are quite different. There's a person who's 45 kilograms, and then there's a rock that's only 3 kilograms, right? Now, the forces on both are equal, right? If I can calculate the force on one, I know the force on the other. The accelerations are obviously going to be different because the masses are different. The only thing other than force that both the student and the rock have in common is how long in seconds they accelerate for. They don't even accelerate over the same distance, right? Because the rock is smaller, it will travel farther in that time interval than the person will because it accelerates to a higher rate of speed than the person does. Does everyone follow me there? The only thing they have in common is time, right? So I'll probably have to calculate that at some point during the problem. All right, so I'm going to write down my givens for both the student and the rock. Sorry, they have one other thing in common. This VI is 0 for both of them. Okay, and final velocity we know for this one as well. It's 9.6 meters per second. All right, so we're trying to find the final speed of the student. So right now, if I want to find anything out about the student, I need either the force acting on the student or the acceleration of the student, okay? My best bet for finding any of those is to find the force acting on the rock because the force acting on the rock is the same as the force acting on the student. Everybody okay with that? All right, if I'm going to find the force, I need to know the acceleration of the student, and I can find that because I have VI, VF, and D. So I'm going to use this formula here. Okay, and solve for A. So I'm going to have VF squared minus VI squared over 2D. So that'll be 9.6 squared minus 0, and I'm going to write that over 2 times 0.6. All right, so it ends up being like 76 or something like that. Okay, so 9.6 squared, whoop, not 96, 9.6 squared, okay, divided by 1.2. Okay, 76.8 meters per second squared. All right, so now I know one more thing. All right, so now that I know the acceleration and the mass of the rock, I can find the net force acting on the rock and thus at least the magnitude of the force acting on the student. So I'm going to go 76.8 times 3, so acceleration times mass, and I'll have the force there. Okay, so 230.4 is my force, 230.4 newtons. So I can bring that over here. Okay, the net force acting on the student is 230.4 newtons. All right, with that number, can I now calculate the acceleration of the student? Yes. All right, so acceleration of the student is going to be 230.4 divided by the mass of the student, which was 45. All right, so 5.12 meters per second squared is the acceleration of the student. Okay, now that I know the acceleration, okay, and the initial velocity, I still can't calculate VF. But we said there was one other thing other than force that the rock and the student have in common, and it is time. I can calculate time with the information I have over here using our old Science 10 formula. Okay, because I just calculated A, now I'm going to use it to get T. All right, so time equals 9.6 minus 0 over 76.8. Okay, so I think we get like 0.110 or something like that. Sorry, 0.125. All right, so the time is 0.125 seconds. Now that I have that, I can bring that over here as well and solve for VF, okay, using the same formula that we have always used before. Okay, I'm just solving for VF now. So VF is just going to equal A times T because VI was 0. All right, so I just take my 0.125 and I multiply it by 5.12, and I'm going to get 0.64 meters per second, and whatever direction that is, it's left. Yeah. Okay. All right, so is there a lot of like convoluted reasoning in that one? I got to get this so I can get this so I can get that so I can go back over and get this thing and then bring it over to that side. Like it's a lot of thinking. Okay, not a lot of difficult math, but a lot of thinking, a lot of steps. All right, I wouldn't give you one like that on a test because I can evaluate whether you know how to use Newton's third law with a much quicker question. Okay, that's basically just testing your mental mettle. Okay, and seeing how well you can kind of work your way through a long problem. All right, what I want to finish off now is, okay, the 2 Newton's second law worksheets. I want to finish off the inclined plane and the forces of vector quantity. Okay, we got to finish those off today because our quiz on Tuesday was kind of Okay, I would have liked it to have gone a little bit better, so we need a little bit more practice on that. Tomorrow, you will get your Newton's second law assignment. Okay, and you'll have all of class to work on it. I'm not going to give you a quiz tomorrow. Okay, you're just going to have the 72 minutes or whatever it is, okay, tomorrow to work on just the assignment. So you should be able to get a pretty good start on it. Like you could be 2/3 to 3/4 done, maybe more, if you focused on it during class tomorrow. Okay, if you're not in class tomorrow, you should be, but if you're not, okay, you're going to have to get it online from Google Classroom. Okay. All right, so back to the forces of vector quantity and inclined planes worksheet. So these are the last few of the inclined planes. And to let you know, 10, 11, and 12, sorry, 11 and 12 have been on unit exams in the past. Okay, so give you some idea of the kind of thing. Sorry, 11 was on a final exam, 12 was on the unit exam. Okay, but those are the kinds of questions that I would ask on a test. So definitely be looking at those. So we got a question about number 4 here on the inclined plane worksheet. All right, so we've got our incline that the car is being pushed upward. Okay, it's being pushed up at a constant velocity. So right off, I'm going to write that my net force is 0 newtons. Okay, I've got a 2,000, what is it? No, sorry, I'm looking for the mass of the car. I don't know what it is. Okay, but I know that there's a 9-degree angle and that there's a force of 800 newtons pushing up a force of friction of 100 newtons, and of course F parallel is always present and acting down the ramp. Now, because the net force is 0, the force up and the forces down add up to 0, which means F parallel has to be 700 newtons. That way I have 800 newtons up the ramp and 800 newtons down the ramp. Everybody follow me there? Okay. Now I can figure out what the force of gravity is on this mass, which will help me to figure out what the mass is. All right, so I know F parallel, I know it's 700 newtons. I know the angle here is 9 degrees, so I'm looking for the hypotenuse. So the sine of 9 degrees equals 700, the opposite side, divided by the hypotenuse. So to get the hypotenuse, I'm going to cross multiply here with the sine of 9 degrees. So hypotenuse equals 700 divided by the sine of 9, and that will give me my mass in kilograms. Okay, so if I take my 700 and divide it by the sine of 9 degrees, I get a force of gravity of 4,474 newtons. If I want the mass of the car, I divide that by 9.81, and I get the mass is 456 kilos. Okay. All right, any other ones giving us trouble? How are we doing with 10, 11, and 12? Need to go over any of those yet? Are we okay with those? Okay, so for number 11, we've got our inclined plane here. Okay, we know the masses. Mass 1 is 2.5 kilograms, 2.0 kilograms. And this one's 2.5 kilograms. All right, the forces involved. I got a force of gravity here that I can calculate. Okay, so I'm going to calculate it right now. We'll have 2.5 times 9.81. All right, so we got 24.525 newtons. Okay, it tells us it's frictionless, but there's still a force pulling down the ramp on the 2 kilogram mass. What is it? F parallel. Right. Okay, F parallel is always present, okay, on an inclined plane. So I've got to calculate what F parallel is. So I have FG, I've got F normal, right? And I've got F parallel, right, which is the thing I'm looking for. Now the angle of the ramp is 30 degrees, so this is 19.62, and then if I go F parallel equals the sine of 30 times 19.62, I'm going to get 9.81. So F parallel is 9.81 newtons. All right. Now I've got to look at this in terms of this is a system. I have all the forces calculated. Right? Now I need to calculate the net force. So the net force acting on this system is going to be 24.525 minus 9.81. Okay, because it's one force going one way, one force opposing it the other direction. Right? So when I subtract those, I get that the net force is 14.715 newtons. Okay, on the system. Now I can calculate the acceleration of the system, not of the individual, well, and of the individual masses without vectors. All right, so the acceleration of the system will be F net divided by mass. So that'll be 14.715 divided by the mass of the system, which is 4.5 kilograms. Okay, so the acceleration of the system is 3.27 meters per second squared. The question doesn't ask for the acceleration of the system, it asks of mass 1. So that would be up the ramp. All right, so just combining what is a relatively simple inclined plane problem with a pulley. All right, so I mean, there wasn't even any friction involved. So all you had to do is calculate F parallel. You had to do an FG calculation and then remember to combine the masses, right? So while initially when you look at that problem, it's like, oh crap, he's combining like pulley and inclined plane. All you have to remember is to combine the masses, okay? And that's it, okay? The rest of it's just an inclined plane problem. So don't let the looks of something intimidate you from being able to solve the problem. Okay, that's definitely a problem well within your ability, which is why it's been on the final exam before. Okay. All right. Any other questions on those sheets? 12? Yep. Okay, so let's start it from scratch here. All right, keywords, constant velocity, meaning net force is 0. Okay, net force is 0. Okay, we know that right off the bat. So F net equals 0 newtons. Okay, so we got our plane, okay, and we're looking for the angle. We don't know what it is. We know that there's a 3,000 kilogram truck, okay, and that there is a force of friction up the ramp of 1,600 newtons. What's pulling the truck down the ramp? F parallel, how big is it? It's equal, yeah. The net force is 0. So the force down the ramp has to be 1,600 newtons. Otherwise, it wouldn't travel at a constant velocity. So once I know that, okay, then I can use the internal triangle here to get the angle of the ramp. Because I know F parallel is 1,600, I can calculate the force of gravity because I know the mass. And then it's just a matter of finding theta using trig. Okay, so we'll calculate what Fg is. So 3,000 times 9.81. All right, it's 29,430. Okay, the sine of theta is the opposite side, which in that triangle is F parallel, divided by the hypotenuse, gravity. Gravity is always the hypotenuse in that triangle. So if I want to find theta, it's just going to be sine to the minus 1 of opposite over hypotenuse. Okay, so that'll be sine to the minus 1 of 1,600 divided by 29,430. Okay, when we do that, we should get 3.11 degrees. Okay. All right, so we still got 5 or 6 minutes here, so if you're not done those sheets, just finish them up. Tomorrow, okay, I think I said this before, but just a reminder, no quiz tomorrow. Okay, even though it's Thursday, there will be no quiz. I want to give you as much time as possible to work on the Newton assignment. So you'll get that right away at the start of class. I'll explain it and then get working on it so you don't have too much homework. Okay. It won't be due till like later in the week after Easter. I'm not going to make it due on the Monday after Easter because you should have a break too. Okay.